Okay, welcome all. So, what's on the program today? I first want to talk about factor graphs. They are another visual means of summarizing how a graphical model, a probabilistic graphical model, factors, and it offers a little more information on the structure of the model than the representation we discussed last time. Next, I want to talk about field of experts as another important category of continuous valued MRFs, which are truly higher order in contrast to the Gaussian Markov random fields we discussed last time. And then finally, I want to talk about discrete valued Markov random fields and what can be done to optimize them exactly. Okay, starting with factor graphs. I showed an example last time. Let me take an easier example. So let's say that we have a potential depending on three random variables, x1, x2, and x3. And I could say that it consists of a product of all of these plus all the pairwise terms. Now, according to what we discussed about hypergraphs and so on, I could represent this in terms of three random variables that are members of one hyperedge. And in this way, I would indicate that these random variables somehow must be evaluated together in one factor. However, I could also choose to give a bit more information, choose a redundant representation, namely, I also have these binary terms. So if I say this is variable 1 here and 2 and 3, I also have this term here, which corresponds to this edge, and I have that term corresponding to that edge, and this term corresponding to the third edge. And I could put that in contrast with some other potential function, let's say psi prime, which has merely this first higher order term. Which would look like this. And if I want to give this more detailed information, I can conveniently use so-called factor graphs. These are bipartite graphs. So factor graphs are bipartite graphs with a set of vertices V for the random variables here. Well, let me use script V to say it's a set. And then script F for the factors, and script E for the set of edges, excuse me. And a single higher order term like the one down here, I could represent by these vertices shown in black, and then a factor, which is typically shown as a filled box. And bipartite means I can have edges only between one set of nodes and the other set of nodes. Whereas up here, I would have this higher order factor, but then also these pairwise factors. And so this shows me a little more about the computation, because I could in principle collapse these lower order factors into the higher order factor, of which their variables, or the scope of which their variables are a true subset. But this more detailed version here shows me a little more about the precise structure of the model. So in such a factor graph, each hyperedge of my original graph, or each potential, is represented by a factor. In this set script f of factors. And each factor is connected by an edge to each original random variable in the scope of its potential function. Okay, and taken together, this gives me this bipartite graph that I mentioned earlier on. Vertices, factors, and edges that may connect only vertices and factors, but not vertices and vertices or factors and factors. In principle, this could be generalized to operand graphs. That is the term chosen by Björn Andres in his PhD thesis, where you can build similar graphs for any potential that is, or for any operation that is associative and commutative. And with such factor graphs, I want to show two things. For example, let's remember the Markov random field that I gave as an example last time. This was the Ising model. So this was the work by Boykov and Jolly. And here's to remind you what these terms looked like. I had unary terms up here. So these unary terms depended on the observation. OI is the gray value at pixel number I. And depending on this observed gray value, you would get a lower energy contribution by either assigning background label 0 or foreground label 1. And then we had a binary term, which I want to, or a pairwise term, which I want to copy now. Well, that's no advertisement here. Okay, so here is the pairwise term used by Boykov and Joly. To remind us, xi and xj were the labels, which could be either foreground or background at pixels I and j. Then theta 1 and theta 2 were parameters. And psi is a potential, so contribution to the overall energy. And whenever the labels differ, this augments our energy. And this augmentation in energy is modulated by the intensity difference. So OI and OJ are the intensities at pixel I and J. And when we are at a place where the image has a strong gradient, then, so this would be the gradient, and this would be this weight function here. Oh, excuse me, it's not a single exponential decay, but it has this kind of shape. So for large image gradients, we will have a small value here, meaning we multiply this entire energy contribution with a small value, and that facilitates label transitions in those areas where the image has a strong gradient. So let's look at the corresponding factor graph. I'm going to show this factor graph for a tiny image. Let's say these are the variables x, and then I want to copy this. And let's say the observations here are friendly purple. These are the observations, and because they are observations, I could also fill these circles just to say that these have been observed. Okay, now we have the unary terms, which were, let's say, psi I, and they depended on the label xi and also on the observation oi. And these unary terms I can now show as factors between each random variable x and its observation. So I have to draw 9 of these now. This will take a moment. Okay, so those are the unary terms. So if we did no smoothing whatsoever, then this would be a pixel-wise prediction of foreground versus background, and we would have no Markov random field. Okay, we would just have independent predictions based on the local. If it's a gray value image, and if we condition just on a single gray value, this would amount to just thresholding at a given gray value level. Okay, and now we have these pairwise terms. So I will now draw factors for all pairwise terms. And like in the Boykov and Jolly paper, I'm using a for neighborhood here, meaning I'm connecting each random variable to only its closest 4 neighbors. The 4 adjacent pixels in north, south, east, west. Okay. And this model here would be correct if I had ignored this last term here. So let me make this last term here in a different color. Okay, it's red now, and if I ignore the red term, then my potentials here, psi ij, would depend on only the labels xi and xj, and that is exactly the factor graph that I've just shown. However, if I now want to also condition on the observations, then my factors will have additional edges. Okay, so this factor here, for example, in front, now depends on the difference between this gray value and that gray value. And it's at this point, at least, that the image is finally going to get very messy. But you get the picture, yeah? So each factor is now connected also to its closest two observations. Okay, I hardly see anything any longer. I think you get the idea, or I hope so. Okay, yeah? No, the white, so the black circles with the white inside are my unobserved states. So those are the hidden states. This is what I want to estimate. So I have an energy which depends on these hidden states, and that is a sum over all pixels of these unary terms plus a sum over all pixels within a 4 neighborhood of these pairwise terms. And x can be either 0 or 1, where 0 is background and 1 is foreground. And these pairwise terms, I can condition them on the observations if I want to, or I can omit that, depending on which formula I use up here. So if I use this modulator here, then my function psi also depends on the observations, which is why I've included them after a semicolon here. Whereas if I ignore the term, then it purely depends on those labels. And the aim is to, or the estimation problem is to minimize all of this with respect to x. Okay, so finding the minimum here, finding the x which minimizes this expression is then my best estimate given the observations O and given, of course, the parameters theta in the model. The pretty purple, where's pretty purple? Those are the observations. In this case, the intensity value or the gray value at each pixel. You asked if I draw it the other way around. What do you mean? Okay. Yeah, you can do it whichever way. Yeah. Okay. More questions? Now, the point I'm going on about this for so long is the principal reason is the following. Namely, there is a fundamental distinction between these two models. If I use only this term here, I obtain a Markov random field, whereas if I also include this modulating term, I obtain so-called conditional random field. So in a conditional random field, or CRF for short, my potentials depend on the observations. So a Markov random field models the probability of the joint probability of the hidden states and the observations, and the CRF models only the probability of x given O, which is less, okay, because This I can rewrite as the probability. Oh, sorry, I wrote it the wrong way around. This I could rewrite as the probability of O given X times the probability of X. No, 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 no. It was correct the original way around. Totally confused now. Okay, here we go. So what I need here is a complete model for the observations, which, if I have it, means I can also sample new observations if I want from the model. But in many cases, I don't want to sample new observations. I'm just interested in the most likely assignment of variables to the hidden states. And this is why we write conditional, which means conditioning on the observation. So this is a simpler task. And if we are only interested in this result, then it makes sense to solve only the simpler task rather than the harder one. However, this is still very closely related to Markov random fields because the probability of X given O is in itself a Markov random field. So as a set of random variables that factorizes according to a relatively simple recipe that factorizes in a sparse way. So if we look again at the black factors here, the pairwise factors. So I had chosen this black for psi ij of xi, xj, and potentially also on oi and oj. These factors here, they always depend on two hidden states. So they are pairwise with respect to the hidden states. However, they can also depend on some of the observations. So in other words, this is a higher order factor. Let me write this in words. This is a higher order factor in general. But if we have observations, so if I have observations OI and OJ, it is merely a pairwise factor. In our case here, pairwise in xi and xj. So this is a big difference. Which can be conveniently illustrated using these factor graphs. So to summarize this part, factor graphs allow to conveniently visualize the internal structure of a Markov random field. And the nice thing is that this works not only for Markov random fields, so for undirected graphical models, but also for directed graphical models. So both undirected and directed probabilistic graphical models. In this lecture, in computer vision, we practically exclusively work with undirected models, but in machine learning in general, directed models play a huge role. So this is a unifying language for both, meaning in particular that you can also use a single piece of software to solve models from, or to infer solutions for both classes. And I want to advertise in particular the OpenGM software developed by Björn Andres and Jörg Kappes and Thorsten Bayer that implements a great variety of algorithms. And you need to specify your model in terms of a vector graph just once and can then very conveniently pick your inference method of choice.